Hey everyone, welcome back to Calculus 3. This will be lecture 15 of the course, and in this section we're going to get into differentials. So we're going to generalize the concepts of increments and differentials. We're going to generalize that specifically to functions of two or more variables. So we obviously talked about differentials back in Calculus 1. And now we are going to extend that idea into the plane. Okay, so let's go ahead and jump into it. So this will be section 3.4, differentials. Okay, so recall from Calculus 1 and 2 that for y equals f of x, function of a single variable x, the differential of y is dy equals the derivative f prime of x times dx. Okay, and so this is what we talked about previously, that this differentiable of y, dy equals f prime x dx. What we're going to do is we're going to extend this into the realm of f being a multivariate. Well, in this case, two variables, f being a function of x and y. So consider z equals f of x comma y, right? So delta x and delta y. Okay, delta x and delta y, you can think of these as the increments of x and y. Okay, so they're the increments of x and y. And then the total increment of z would be given by the total increment of z would be delta z equals f of x plus delta x, y plus delta y, minus the starting point, right? So you've moved x and y slightly, and to find the total increment of z, you would have to subtract that off, right? So let's, kind of using this as a starting point, let's talk about what we mean by the differential. What we mean by differentials of a function of x and y. Okay, so let's get a definition here. So if z equals f of xy, and delta x and delta y are increments, they're increments of x and y. Okay. Then the differential, differentials of z, is what? Well, it's dz equals, now you're going to take the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. And another way to kind of notate this, maybe possibly a more convenient way depending on your inclination, would be to use the f sub x notation. Like so. Okay, so that's the idea. So if z is a function of x and y, and delta x and delta y are the increments of x and y, so this is the nudge you're giving x and y respectively, then the differential of z is this, right? So it's basically the partial derivative times dx plus dz, but partial derivative of y with times dy. Okay, so let's do an example. Let's see how this spins up in an actual example. Okay, so let's find the total differential for the function z equals 2x sine of y minus 3x squared y squared. Okay, so the differential dz, again, we just defined it, is del z del x times dx plus del z del y times dy. Okay, and so we have to differentiate with respect to x first. And so going through this, that's the partial derivative with respect to x. So you would get, let's see, so basically everything in here is a constant except for x. So you'd get 2 sine of y, and then this would be minus 6xy squared. That's times dx, right? And then the other one would be similar idea. We would just go through and differentiate with respect to y first. So that would be plus, and then it would be 2x cosine of y minus 6x squared y dy. Okay, so that would be the total differential for this function z. Okay. Let's do the same thing for a different function, just so we can make sure we have to understand the mechanics of this. Okay, so let's try another example. Find the total differential for, here we'll say w equals x squared plus y squared plus z squared. So here you've got w as a function of x, y, and z, right? So the definition will naturally extend into into functions of 3 independent variables as well. So the total differential here would be dw equals, let's write out the formula first, del w del x times dx plus partial derivative with respect to y dy plus partial derivative with respect to z dz. Okay, and so we could easily go through and differentiate this, right? So when we take the partial derivative with respect to x, these are just constants, so that's just 2x dx, and then it's 2y dy and 2z dz. Okay. All right, so there's two examples of calculating the differential given the function. Okay, so previously we've discussed how, given a function y equals f of x, if it's differentiable, we could use the differential as an approximation for small delta x, okay, to the value of dy. So previously, given y equals f of x, if it's differentiable, we can use the differential, and specifically in the case of the single variable, it'd be dy equals f prime of x dx. We can use that as an approximation, and this of course only really works for small dx, right? For small delta x, for small increments in the x value. So we could use it as an approximation to the value delta y equals f of x plus delta x minus f of x, right? Right. So this is kind of like, well, this is what we talked about back in calculus 2 when we talked about differentials for the case of a single independent variable. We can extend this naturally into differentiable functions of 2 variables. Okay, so let's do that. Let's flush out what the definition looks like in this case. So a function f given by, z equals f of x, y is differentiable. It's differentiable at some point x naught, y naught if delta z can be expressed in the form, right? So here's the form. Delta z needs to be expressible in the form delta z equals f sub x evaluated at the point x naught, y naught times the x increment delta x plus f sub y evaluated at the point x naught, y naught times delta y plus some epsilon increment plus some other epsilon increment in the y direction. Okay, so the total differentiable, the total increment delta z needs to be, if you can express the total increment delta z in this format, then your function f is differentiable at the point. Okay. Now notice here both epsilon 1 goes to 0 and epsilon 2 goes to 0 as the increment decreases to 0. So as delta x, delta y goes to 0, 0, right? So as the increment gets smaller and smaller, then these epsilons need to vanish. Okay. And so that's what it means for a function of two variables to be differentiable at a point. And then of course, this definition can get extended to being differentiable on a region if the function is differentiable at every point in the region. Okay. So let's do an example where we show that a particular function is differentiable. Okay. So let's do an example here. So let's show that f of xy equaling x squared plus 3y. Let's show that this is differentiable at every point in the plane. Okay, so how do we go about that? So how would we go about showing that this is the case? Well, let's let z equal f of xy, okay, obviously. Then the increment of z at an arbitrary point xy in the plane could be written as this, right? So the increment of z at an arbitrary xy can be written as, right, how can we write it? Well, so you would have your delta z, right? The increment of z is going to be basically equal to f, and then x, the arbitrary point you're given, plus whatever your x increment is, and then y plus whatever your y increment is. Okay, and then of course minus your starting point. All right, so this is going to represent the increment in z, that whatever that movement is. Okay, and we can just expand this. Well, let's plug the function into this expression and then expand it. All right, so this would be x plus delta x squared, right? So taking x plus delta x and plugging it into this function everywhere you see x, and then that's going to be plus 3 times y plus delta y. Okay, so that's this piece, right? And then minus the function itself evaluated at x and y. So minus x squared plus 3y. Okay, and then we can just expand this. And we get what, x squared plus 2x times delta x plus delta x squared. Right, so that's just foiling out this guy. And then plus 3y plus 3 delta y, and then minus x squared minus 3y. Okay, and then obviously a lot of things are going to clean up, cancel out here. So the x squares will disappear. The 3y's will disappear, and so you're kind of left with these three pieces here. So you have 2x times delta x plus 3 times delta y. And then instead of delta x squared, I'm going to actually write this as delta x times delta x. Okay. And now one thing that's not here. Well, okay, let's stop here for a second. All right, we'll pause before we jump to the next part. So notice that, you know, the given function was f of xy equals x squared plus 3y. So what are the partial derivatives of this? So we'll come back to this. So pause. What is f of x, xy? Well, it's just going to be 2x, isn't it? Okay. So, and then what is the partial derivative with respect to y? It's just 3, right? This is a constant, so that derivative is just 3. Okay. And so notice here that this piece here, that's your partial derivative with respect to x. This piece here, that's your partial derivative with respect to y. And then what about this guy over here? Well, this is one of those epsilons. You know, this is one of those epsilon increments, right? So let's pick this up here. All right, so what I have here is I have f sub x, xy, times my delta of x, that's this guy, plus partial derivative with respect to y, times delta y, that's this guy. And then this delta x, you could write that as epsilon 1 times delta x. Remember, epsilon is a small value, right? And specifically, epsilon will go to 0 as delta x goes to 0, so that's clear there. Now, what's missing here is the delta y, right? But we can always just write this, plus 0 delta y, right? And so this whole thing has the form that we want. So we have our epsilon 1 delta x plus our epsilon 2 delta y, and it's obvious that epsilon 1 goes to 0 and epsilon 2 goes to 0 as delta x, delta y go to 0. Okay, and so that means this function is differentiable. Okay, it's differentiable, right? And specifically because it has this form. This is the form of the differential for a function. Okay. This is the form of delta z that delta z needs to take. Okay, so that's how you would do that. So it's basically just a kind of, in the case of trying to show something like this, it's really, you know, remember what this is, plug it all in, and recognize that that total increment better be equal to something of this form, right? So your partial derivative is going to have to drop out and be times delta x. Your partial derivative with respect to y is going to have to drop out and be delta times delta y, and then you're going to have these two other pieces, or they could be absent and just 0, but anything remaining is going to have the quality of going to 0 as the increments go to 0. Okay, and so in that case, then you have shown differentiability. Okay. All right. Very good. Very, very good. So differentiable. So there's a little more burden when talking about differentiability for functions of multiple variables, or functions of two variables in particular for what we're looking at. So when we say differentiable for a function of one variable, basically what that means is that the derivative exists. So if a function is differentiable at a point, it just means that the derivative exists. But for two variables, we need more than just the existence of the two partial derivatives. And so the next theorem will give us some insight into that, right? So for f of x, differentiable means the derivative exists. But for f of xy, we need more than just f sub x and f sub y existing. Okay, so we'll need more. Okay, so let's jump into this theorem, right? And so this guy says that if f is a function of x and y, where the partial derivatives are continuous in an open region R, where basically f of x, f sub x, and f sub y are continuous in an open region R, then f is differentiable on R. Okay. So this theorem basically tells us that we can choose x plus delta x and y plus delta y close enough to xy to make epsilon, to make those two leftover pieces, epsilon 1 delta x and epsilon 2 delta y, to make those two pieces insignificant. Okay. Right, so in other words, for small increments of x and y, we can use the approximation delta z equals dz. And previously we saw that dz equals del z del x times delta x plus del z del y times delta y. Where, of course, the partial derivative with respect to x is going to represent the change in the slope in the x direction, and the partial derivative with respect to y is going to represent the change in the slope in the y direction. And so dz here is going to represent the change in the height of the plane that is basically tangent to the surface at the point. Okay, so dz represents the change in the plane that is tangent to the point of interest. Tangent to the surface at the point of interest. Okay. All right, so that's kind of an intuitive, reasonably intuitive way to think about this. Let's do some examples. Let's do some examples here. All right, so the first example we'll do is let's use dz to approximate the change in, and here's the function, z equals 4 minus x squared minus y squared. We want to approximate the change in this as xy moves from the point 1, 1 to a very close point, let's see, 1.1, 1.01, comma 0.97, right? So a neighboring point. Okay, so we want to approximate the change in this function as xy moves this little distance. Okay, so how could we do that? Well, we can use what we've just talked about. So let's let, all right, we'll start with defining our xy as 1, 1. Okay, and that means our x plus delta x and y plus delta y, that's going to be equal to 1.01 comma 0.97, right? So the starting point, the point you move to. Okay. And so we can plug these into the expressions we previously talked through, and we can easily get to a dx, which is our delta x, which is basically 1.01 minus 1, so 0.01. And the same thing for our dy, which is our y increment, and that would be equal to 0.97 minus 1, which would be negative 0.03. Okay, so we have these small increments. And then the change in z can be approximated it can be approximated by what is the form here? Well, it's delta z is approximately dz, right? And it's going to be, what's that going to be equal to? Well, that's the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. And so we didn't find the partial derivatives yet, but it's real easy in this. This is 4 minus x squared minus y squared to the 1/2 power, and so we can easily crank those out. And so the partial derivative with respect to x is going to be 1 over this, and then the chain rule says you got to differentiate inside, so you get negative x as well, right? So what you end up with here is negative x divided by the square root of 4 minus x squared minus y squared, okay, times delta x, plus, and then the same thing but for the partial derivative with respect to y, you get a negative y over 4 minus x squared minus y squared still, sorry about that, and then a delta y. Okay, and so then you can evaluate this function, right, by plugging in these quantities here and then the x values. You can approximate this increment. And so that, basically when xy is equal to 1, obviously that implies that delta x is 0.01 and delta y is negative 0.03. Okay, so you can plug all of this in, and you get a delta z that is approximately equal to, so this would be, all of the x's and y's would all be 1 here, so this would be negative 1 over the square root of 2 times your delta x, which is 0.01, plus, and then this would be negative 1 over the square root of 2 again, times your delta y, which is negative 0.03, right? And you can add all of this together, and you would get 0.02 over the square root of 2. Okay, so some really small number. Okay, so that's some really small number. Well, it's like, 0.01-ish, maybe 0.014-ish. Okay. All right. Excellent. Okay, so let's look at another theorem here quick, and then we'll do a couple more examples. So here's another theorem, and we'll just state this, and then we'll talk about it. Okay, so if a function of x and y is differentiable, okay, at some point x naught y naught, then it is continuous at that point. Okay, so if a function is differentiable at x naught, y naught, then it must be continuous there as well. Okay. So remember, I mean, this kind of harkens back. Remember that the existence of the partial derivatives at a point is not sufficient to guarantee the differentiability of the function, okay, at the same point. The function, so what this theorem basically tells us is the function has to be continuous as well. Okay. So in order for a function to be differentiable, the partial derivatives do indeed have to exist, and the function has to be continuous at the point. You can run into instances where the function is not continuous, but the partial derivatives do exist. Okay, so let's see an example where that's the case. Let's see an example. So we're going to show, so let's consider this function. Consider f of xy, where the function is negative 3x over x squared plus y squared, or it's 0. Okay, and in particular, it's 0 whenever x and y are both 0. And it takes this form whenever xy is not 0. Okay, so what we're going to do is we're going to show that the partial derivatives of this function exist at 0, 0. Okay, but that f is not differentiable at 0, 0. Right, so this is not something you would expect to see if f was a function of a single variable. Right, if this was a function of just x alone, then we wouldn't expect the derivative to exist, but the function to not be differentiable. Those two go hand in hand. But in the case of multiple variables, it is possible for the partial derivatives to exist, but then to have the overall function be non-differentiable due to continuity issues. So what we'll show is that del f del x and del f del y exist, but f is not differentiable. Okay. And so to show that it's not differentiable, we can just consider the continuity of the function. And specifically, we're interested in the point 0, 0. And these should say 0, 0 here, sorry. Okay, so let's see, we'll show that f is not differentiable because it is not continuous, and this is specifically at 0, 0. Okay, so how could we show that it's not continuous at 0, 0? Well, we talked about this a bit as well when we were discussing continuity of multivariate functions like these, where in the case of a single variable, continuity is really what you need to show is, in order, one of the conditions of continuity is that the left and right hand limits need to agree, right? So whether you approach a point from the left hand side or approach the point from the right hand side, the limit needs to be the same if the function is continuous. Now, what we saw in the case of multiple variables is if we have a region and some point, we need to be able to approach that point from any direction and have the variable be the same. Or sorry, have the limit be the same. And that's what we can exploit in this particular example. Right? So let's consider first on approach, and again we're approaching 0, 0, on approach to 0, 0 along the line y equals x, right? So in the plane you're going to have the y-axis, you'll have the x-axis, and then there's going to be some line y equals x, which is namely the diagonal, right? So if I approach 0, 0, which is the intersection of the x and y axes, if I approach that on the line y equals x, then what happens? What does the limit look like? Well, the limit as xy approaches 0, 0 of the function will be equal to the limit as x comma x approaches 0, because remember, y is equal to x. That's the line I'm on. I'm approaching on that line. Okay, now what does that give me? Well, let's plug in the function. So this is the limit as x comma x approaches 0 of, and then the function is negative 3x over x squared plus y squared. And sorry, this is 0, 0. Keep writing that. Okay, so what is this going to do? Well, this is going to be hold on a sec, did I write this down wrong? 2x squared. Yeah, no, that's okay. So this is going to approach the point negative 3x squared, and then the bottom will be just what, 2x squared? Yep. Right, because this will be x squared and that'll be x squared. Add them together, you get 2x squared. Okay. And so this guy is going to go to negative 3/2, isn't it? Okay, and so that's the limit as you approach the point 0, 0 on this function along the line y equals x. But what happens if we approach from a different line? Next, consider an approach along y equals negative x, right? So in the xy axis, first we approached it like this. Now let's approach it like this. Okay, same point. And so what happens then? Well, you've got the limit as xy approaches 0, 0 of the function f. That's going to be equal to the limit as x comma negative x approaches 0, 0 of the function. Okay, and what happens in this case? Well, in this case, I think I wrote this down. I think this is supposed to be 3x squared. Yes, it is. Yes, sorry about that. That's where this is coming from. Oh, sorry, no, it's 3xy. Sorry about that. That should be 3xy. That's probably throwing everybody off, right? So, okay. And so, yeah, sorry. So that's where the x squareds here come from. And so this would be equal to the limit as x comma negative x approach 0, 0. And so what do we end up with there? Then we have the limit as, well, let's just write it in here. This will be negative 3, and then you've got your x, and then you've got a negative x, right? Divided by, again, the denominator would be, you've got x squared plus negative x squared. So again, it's going to be 2x squared, right? Okay, and so then that gives you basically negative 3/2, or positive 3/2, because the negative and negative, that's the difference. Okay, and so as you approach it along the line y equals negative x, you get this limit, and when you approach it along the line y equals x, you get that limit. So the limits do not agree for all approaches. And so what does that mean? Well, that implies then that not continuous at 0, 0 in particular, right? That's the only one we've looked at, but this function has a continuity issue at 0, 0. Okay. All right, so we've shown that it's not differentiable. Now, kind of the point of an example like this is to not only show that it's not differentiable, but to show that the partial derivatives exist. And so this kind of distinguishes differentiability in 2 dimensions, or in 3 dimensions, versus differentiability in 2 dimensions. Right, so we just saw, approaching 0, 0 from 2 different lines results in a different value for the limit. Therefore, f is not continuous, and therefore f is not differentiable. But the derivatives exist. the partial derivatives exist. Okay, let's see that. Okay, so let's take the partial derivative at 0, 0 with respect to x. This is going to be equal to the limit as delta x goes to 0 of f of x, f of delta x, comma 0 minus f of 0, 0 divided by delta x. All right, now what's going to happen here? Well, this is going to be 0 minus 0 on top, right? We know that. Well, shoot, I need to write the other part. So limit as delta x goes to 0 of 0 minus 0 over delta x. And so this will just be the limit as delta x goes to 0 of 0, which is just the 0, right? So the partial derivative with respect to x exists at the point 0, 0, right? It has a value of 0. What about the partial derivative with respect to y? Do we get the same thing? Yeah, pretty much, right? Same kind of idea. So this is the partial derivative with respect to y at the value 0, 0, at the point 0, 0. It's going to be equal to the limit as delta y goes to 0 of f of 0 comma delta y minus f of 0, 0, all divided by delta y. And again, like we saw, this is 0, this is obviously 0, and this is 0. Right? So this one is 0 because the value of x and y is equal to 0. This one is 0 because you can, anytime you have a 0 as an x, you're going to end up with a 0 in the numerator. So you get a 0 in the numerator here, you get, by definition of the function, a 0 here. Right? So this is 0 minus 0. Okay, and so of course you subtract the zeros first, and that makes the whole thing 0 automatically, and then the delta y going to 0 has no bearing, and so again, the derivative exists. And the fact that they're the same is nice too. Okay, so here's this was an example. Del f, del x, and del f, del y exist, but the function is not differentiable in the sense that, for the reason that there's no continuity at the point of interest, 0, 0. Okay, all right, so I know that's kind of a handful, but differentials are important tools in calculus. They can be a little strange at times, but I think hopefully that was straightforward relatively. So that's where we'll end it, and in the next lecture we'll get into the chain rule. We'll talk about more derivatives in functions of multiple variables, specifically the chain rule. Okay. All right. Until then, take care.